let me first thank organizer for organizing the event and letting me share my research with you. So today I'm going to talk about interfacial processes in lithium-ion batteries. And we had a talk today about lithium-ion batteries, so I will skip some of the fundamentals about lithium-ion batteries, but I will emphasize some part of that. Let me acknowledge some people. So Maria, actually, Chan and Jeff Greeley did some DFT calculation for us in Argonne, so I will show some of those data. Maria is actually one of undergrads in our group. She did some of the MALDI experiment. I will show you some of that stuff. And David Cahill actually is our collaborator. We use the stress measurement setup, actually, in that room over there. We're there. And so let me start with that. Okay. So lithium-ion batteries, Daniel Abram explained how lithium-ion battery works. So let me emphasize a couple points. First is, as Daniel said, it's a rechargeable battery. So you have exchange of lithium between two electrodes. So you're putting lithium into one electrode and removing that. Ideally, this thing should be very reversible. And another thing I want to emphasize is, as you exchange lithium between electrodes, you form an interface on top of the electrodes, and especially anode, which is the negative electrode. And we call this thing solid electrolyte interface. And I will emphasize the solid electrolyte interface throughout my talk. And here, I'm just showing that. So we have a stability window for each electrolyte we use, right? So if we go lower than a potential limit, we start oxidizing and reducing that electrolyte. So now we form a CI layer on top of two electrodes. Then that will give us a little bit more higher window that we can go, because that's a protective layer on top of the electrode. So we can have extended window of potential. So this SEI layer is an amorphous layer, so it has a lot of different things in it: inorganic compounds, organic compounds. And that thing, we want to see what is the mechanical effect of this layer on the electrode in lithium-ion battery anodes. So people have done a lot of studies on SEI, and they showed that it's a very complex mixture of inorganic compounds and organic compounds. And they did spectroscopy, XPS. So the basic message of all of these studies was that it's very complex. Because if you have organic compounds, they are actually repeating units. They are some sort of polymer or something. And you're not going to get that much spectroscopy data from those, because they are exactly the same thing. You're repeating the same thing. And in inorganic compounds, because we are in a very reducing environment, it's actually very complex to interpret a lot of spectroscopy data. Okay, with that, I'm going to explain how we are going to measure the mechanical changes on the surface of the anode material in lithium-ion batteries. So this is the setup we use in David Cahill's lab, and Jim Langer was actually the student who showed me how to work with this instrument and actually helped me a lot at the beginning. So the basic of the method is we have a very thin cantilever. So this cantilever is around 150 micron. So as the surface stress of the substrate changes, the cantilever will start bending. And if we reflect the laser from the surface of the cantilever, we can detect how much the cantilever is bending. And that bending of the cantilever is related to the surface stress of that material through the Stoney's equation. Okay. So some other group actually did some studies with different methods on surface stress changes on lithium-ion battery anodes. And especially on silicon. So the important thing about silicon is because you have a big expansion as you put lithium in and out of the silicon substrate, you will get a lot of stresses on the surface, and a lot of stress is developed on the surface of the silicon. And the bottom line of all of these studies was that as you put lithium inside the anode material, you develop some compressive stress on the surface. And as you remove this thing, you pretty much remove this compressive stress. But the point is, especially on silicon and on this high capacity material, because you have a lot of expansion and contraction, you start breaking the surface as you put lithium in and you remove it, especially if you have single crystalline silicon. So the system we chose to study this effect was gold. And gold was, for us, was a model system for an anode material in lithium-ion batteries. So and what you can see here is a cyclic voltammetry. So what we are doing here is we're cycling from 2 volts, and we are going to more cathodic potential, so lower potentials. So ideally, if you get very close to 0, you are going to the bulk deposit lithium into the gold. But we are not going in this graph here, we are not going that low in the potential. So we are not bulk depositing lithium into the gold. But the point is we are seeing a couple features here. One here, and one over there. So people previously studied this system and assigned this peak to lithium UPD and that peak to the stripping of the lithium UPD. And they said, this peak is pretty much reduction of the solvent and electrolyte. This is, as I emphasize here, that this is a very reducing environment. So this is 2 volt versus lithium. In the surface stress, what we can see is, as other people reported, other material on gold also, as you go to lower potential, you develop that compressive stress. And when you come back to the anodic potential, you remove that compressive stress, come back exactly where you started. And the magnitude of the stress from beginning to the end is around 6.5 Newton per meter. If we get the derivative of the stress versus potential, we will see a couple more features that they are not shown in the cyclic voltammetry. So this is not a very simple process that you just put lithium in and out. So something else is happening on the surface. So we wanted to know exactly what's happening here. So we went and we studied more on the electrochemistry of the system. So we started at 2 volts, and we switched the potential at different potential to see exactly where this peak happens. So where this peak starts showing up. And you can see that even before this peak, if we switch before that peak, we still have that feature in 1 volt. So this means that this peak, whatever it is, it's not lithium UPD. So it's not related to putting lithium in, because even before that peak, we are getting some lithium out of the surface. And if we get another material that is different than this system, so this system is lithium perchlorate PC, so if we get an ionic liquid, that the ionic liquid is supposedly more stable toward reduction in this environment, and you don't see that much reduction of the ionic liquid, so you can see there's no peak over there. So that peak is probably related to solvent or electrolyte. Oh. And another important thing here is that the amount of lithium we're putting in and removing from the surface is more than monolayer. So here we have around 6 monolayer of lithium putting in. And this is not like other UPD system. In UPD system, we usually deposit just a monolayer of lithium. So this shows that we are forming some sort of surface alloy on the surface. So lithium and gold are alloying on the surface. Jeff Greeley and Maria Chan, they did some DFT calculation and to show how much stress is developed if we put just a monolayer of lithium on the surface of the gold. And what they actually, bottom line, their result was that the lithium has a very high tendency to alloy with the gold. So lithium wants to be surrounded by gold atoms. So because of that, the full monolayer of lithium is not stable. And we will show that because of that, you can see this full monolayer of lithium. So here is the voltage and coverage. The full monolayer happens at 0 volts. But we will see that experimentally, that the bulk alloy formation of lithium and gold happens a little bit higher than 0 volts. So it means that this full monolayer is not stable, and before getting to that potential, gold and lithium start alloying themselves. But the point here is calculation also shows that as we increase the coverage of the lithium on the surface, we develop some compressive stress on the surface. The value of the stresses is less than the experimental value, and the reason is this model is just for a monolayer of the lithium. But in the experiment, we showed that we had at least 6 monolayers of the lithium on the surface. Okay, so as I said, that was a surface alloy formation. So what will happen if we go lower in potential? So as you can see, if we go lower in the potential, we start bark depositing lithium in the surface. And if we compare these peaks over here in current with this peak over here and there, you can see the current over there is a lot less than these currents. So here is we have like 10 microamp per centimeter squared. But when you get to bar, we had at least 500, even 1 milliamp per square, per centimeter squared. So these are different phenomena. So this is surface alloy formation, but if you go low in potential, then we have the bulk alloy formation of lithium and gold. So now the question is, what will happen with the surface stress? So when we get to these potentials, and when we cycle, we go negative in potential, we put lithium into the surface. When we come back anodically, we remove that lithium, and we develop the compressive stress. We remove that compressive stress. But unlike the surface alloy region, now we have some residual stress on the surface. So unlike that system that it went back exactly where we started at the beginning of the cycle, now we have some residual stress developed on the surface. And we wanted to know what is the reason for this residual stress. So if we continue cycling, so that this is the first cycle, some residual stress, second cycle, even more residual stress on the surface. So we wanted to know what's happening here. So another technique we used was QCM, electrochemical QCM. So basically, which is quartz crystal microbalance. So the thing it does is it actually measured how much mass you put on the surface as you start cycling. And we can see, as we start cycling, during each cycle, we are putting some extra mass on the surface. And this extra mass is the SEI layer that I mentioned at the beginning of the talk. So you are putting a layer on top of the anode, that's the solid electrolyte interface, that has a mass that we can see it in QCM. And we think that this SEI is actually cause of this residual stress on the surface, that we didn't have it in the surface alloy, because in surface alloy we don't form that much SEI. But when we get to the low potential, then we are forming more and more of this SEI layer, and this actually causes that residual stress on the surface. So we showed, recently that a big part of this SEI is a very long chain polymer, and this is a multi-matrix assisted laser desorption ionization mass spectrometry. With what it does is actually it can ionize very big ions, so polymers, so ions with a very high mass ratios. And you can see here after first cycle we have polymers that develop on the surface with mass ratios to 2,500. And even if you continue cycling, you have even 3,500 mass ratios of the polymers on the surface. And we showed that the structure of this thing is something like that. So it's a polymer with this type of structure on the surface. Okay, so I already said that the SCI causes this residual stress on the surface, but how it does that? So in the beginning, so in this surface alloy formation region, so we go lithiation, we develop the compressive stress. When we remove lithium from the surface, we remove that compressive stress from the surface. When we go back exactly where we end up. So this is a reversible process. So we can put the lithium in, remove the lithium, we will get exactly where we started. Now, if we go to the bulk lithiation region and we form the SCI, so we go compressive when we lithiate, but when we remove the lithium from the surface, because we now have this polymer in the SCI, so this polymer actually contracts the surface together and develops the tensile stress on the surface. And this is how this tensile stress is developed when you go low enough in the potential. Now we wanted to know why exactly, is there any way that we can show why it's not forming here when we are in the surface alloy region? And when we did, we went and did actually multi experiment in different potentials. So when we take it, when we start from 2 volts, in 1 volt we take it out, take a multi experiment, there's not much on the surface. At 0.3 there's not much on the surface. 0.15 even there's not much on the surface. But if we come back, we start anodic potential, we can see there are some polymers forming on the surface as soon as we reverse the potential and go to the anodic direction. And this shows that that SCI polymer actually forms during the lithiation of the surface. So when the lithium is removed from the surface, at the same time, long-chain polymers are formed as part of the SCI. And this is the reason for that residual stress in the surface of the gold electrodes. Okay, with that I will come to my conclusion. So in conclusion, actually, one of the most important thing in my view with that thing was in the surface alloy formation region was that people previously thought that lithium will form a monolayer on the surface of the gold, but that's not the case. Lithium and gold with alloy at the beginning of the potential window, and that alloy formation is not a monolayer formation, so it's a multi-layer alloy formation, surface alloy formation. And we also showed that if we do first principle calculations, we can show that there's a compressive stress development on the surface. And the values are not exactly the same thing, but the calculation model is just a monolayer. But we showed that there are more than monolayer lithium formed on the surface in the surface alloy formation region. And when we go to the full lithiation SAI formation, because of that irreversible formation of the SCI, we develop a irreversible tensile stress on the surface. That's a residual tensile stress on the surface that we can contribute to the polymers on the surface in the SCI layer. And with that, I will come to my acknowledgement. I will acknowledge my advisor, Professor Gors, and our collaborator, Maria Chen, Jeff Greeley, Glenn Ferguson, and Larry Curtis in Argonne National Lab. Maria and Jeff, they were my undergraduate student working with me. And Joe is our QCM expert in our group. And Dr. Yao actually helped me with a multi-experiment in mass spec center of the chemistry department. And all the Ghost group members, my fellowships, and Department of Chemistry, and funding agency. Thank you very much for your attention.